so much for coming out in this rainy weather to see one of our next lecture speakers. My name is Steph Guerra, and I am a co-director of Science in the News. For those of you who don't know, the goal of Science in the News as a graduate student organization is twofold. First, we're aiming to bring science to the public, people like you, and also we like to train our graduate students to be better able to communicate their science. And so we do this in a number of ways. First is through the seminar series, so we made it to one of our events. And this is what's happening right now, and we have a whole series that's going on, so please pick up a flyer and come to our remaining 3 lectures as well. Additionally, we have an event known as Science by the Pint, and so this is an event that occurs at a bar called the Burren up in Davis Square, I believe. And so the Burren is generous enough to let us come there and bring scientists to a bar, and you can sit around and chat with scientists over beer if you're of age, of course. And then besides that, we also have a brand new initiative, which is an art gallery, which showcases different images that are created by scientists in their lab every day. And we have a new Instagram, so please follow us on there to see those images. And we also, lastly, have a blog, which we practice our forms of written communication and have a lot of really good short and long form articles there. So we really run the gamut of all the different events that we hold, and we hope that you're able to enjoy those and follow us on Facebook and Twitter to see more things coming from us in the near future. And I'm Jess. I'm the other organizer of the spring lecture series. And so I'll introduce a little bit more about our series. We do have three lectures left, so hopefully you can make those. They'll be every other Wednesday, and at the same time, same place. And the format for tonight's lecture is that we have about 3 different question breaks at which you can ask questions. So we do ask that you save your questions for the question breaks. And at the second one of those, in the middle of the talk, we'll also have an intermission for about 10 minutes where you can use the restroom or get some refreshments, and we'll ask further questions of the speaker. So that'll come up, and then in the meantime, you sit back and enjoy the lecture. Thanks for coming tonight. So here's Laura.
Thanks for coming, everybody. My name is Laura Schaefer. I am a 4th-year graduate student in the Department of Astronomy here at Harvard, which is located on a separate campus from this one, with the Smithsonian Institute for Astrophysics. To give you a little bit about my background, I was a researcher in a planetary science department for about 10 years before I came to graduate school. In that time, as I was working in planetary science, where people tend to work more on solar system objects, astronomers had really gotten into the planetary science game because they started discovering planets around other stars that we call exoplanets. And I got really interested in those, and I decided to come get my PhD here, where we have some world-class researchers into exoplanets. So here I'm trying to kind of mix those 2 worlds, and I'll talk about a little bit about how we can apply geology, our understanding of geology and the objects in our solar system, to looking at exoplanets and our goals for those objects. So here's a little bit of a roadmap for this evening. So in the first part, I am going to talk all about water, and in particular, I'm going to tell you about why we care about water, astronomers and planetary scientists, and where you can find it in the solar system. The second part of the evening is about Goldilocks and the 3 planets. And the 3 planets I'm referring to there are Venus, Mars, and Earth. And then I'm going to tell you a little bit about how we hunt for exoplanets, and how many we have found them, what they're like, and the detection methods that we use to find them. And then in the final section, I'm going to describe how my research kind of bridges these subjects and talk about super exotic planets might have water on them. So that's my one and only Mary Poppins reference for the night, I promise. So the first section is going to be about where's the water in the solar system. And first, I want to talk about why do we care about water so much? And if you go to any astronomy talks about exoplanets, we're always talking about water. And the reason is that we think that water equals life, at least on the Earth. So water provides the solvent that allows all the chemical reactions that occur in your body and all living forms of life on the Earth that we know. You yourselves are about 65% water by weight. 70% of the Earth's surface is covered by water. So if we're trying to find life elsewhere in either our solar system or further out into our galaxy, we first think that we need to look for water. Now, you might think that that's a little bit short-sighted. Maybe there are forms of life that don't depend on water. But, and that might be true, there are people who are thinking about other ways to find life, other different kinds of chemistries that life might have. But the fact is that this is the only kind of life that we know. And it's going to be the easiest, therefore, for us to identify. And there's a couple of other pretty good reasons, we think, why water might be a pretty common requirement for life throughout the galaxy. So why water? Water has some unique properties. First of all, solid water floats in its own liquid. So, as we see here, these happy little penguins are on this floating chunk of ice. And why is that important for life on the Earth? Well, it provides environmental stability, which is why you can go fishing in the winter, in ice fishing. So water freezes, lakes freeze from the top, and the water remains liquid below it, and that allows the fish and the other organisms within that ecosystem to survive extreme ranges of temperatures. So environmental stability is one very good reason why water might be very important for life. Another reason water might be very important is because it's a polar molecule. And polar just means that it's got a slight, the electric charge of the molecule is not evenly distributed. So here we have a very happy little oxygen molecule that's mostly negative, and we have two little hydrogen atoms that are mostly positive. And this allows for membrane formation. So membranes are these special class of organic molecules that have this positive hydrophilic head and these negative, very long tails. And in very natural systems without biology, you can get membranes to form. And membranes are very important because they are what surrounds all living cells on the Earth. So that's a very easy way to compartmentalize chemistry and keep it contained in water. Helps that happen. That happens very easily in environments on the Earth. A third reason water is very important, we think, for life is that it's liquid in ranges of temperatures favorable to the formation of molecules that we find in living objects. So here in this figure, I'm showing what's called a phase diagram. So on the x-axis, we have temperature, and here on the vertical axis is pressure. And these lines show where water changes between the solid phase, that's ice, and a gas, or a liquid. So as temperature increases along with pressure, constant pressure, water will change phase. Now, the Earth's atmospheric pressure is about here. So this is about the Earth's atmosphere. And we have a range of surface temperatures on the Earth. As we all know, in Boston, it can get very cold here. And so we're very familiar here in Boston with the solid form of water. We wish it would go away. But normally, most of the Earth's surface is in this region of temperatures where water is a liquid. And in certain environments on the Earth, we can get hot enough temperatures, like on your stove, where we can turn water from liquid into a gas with boiling water. Now, other planets in the solar system don't have the same pressure. So if we take, for example, Mars, its atmospheric pressure is down here. So on the surface of Mars, water can actually not be a liquid. It's either a solid. In certain regions of Mars, it can get hot enough that that solid turns directly into a gas, but it never actually passes through the liquid state on Mars today. So these are 3 reasons why we think water is important for life. And another very important reason that we search for water everywhere is because, quite frankly, we find it everywhere. So in the galaxy, the most abundant elements in the galaxy, in the universe as a whole really, are hydrogen, which is the most abundant, and that's what most stars are made out of. Helium is about 20% as abundant as hydrogen. And the next most abundant element is oxygen. And here we have a photograph of a galaxy taken by the Hubble Space Telescope. And the central portion of this galaxy is actually made out of superheated water vapor. And that water vapor is emitting a lot of light, and so it glows very brightly here. So we find water vapor all over this galaxy. We also find water all over our own solar system. So here's a photo. I don't think you can see it very well. You can kind of see that. Okay, so I have a funny story about this slide, and it's too bad you can't really see it very well. Is that better?
Yes.
All right, so you can see the photo now. So I had a funny story about this slide. I was showing my boyfriend my slides before this talk, and I showed him this one, and I was like, this is my favorite. This is my favorite slide. This is so cool. And I kind of skipped past it, and he was like, wait, why? That's kind of lame. You just kind of like photoshopped a couple of random objects together there. And he's like, no, this is actually really, really cool. It's not Photoshop jumble of images together. And then I explained what it was, and he's like, oh yeah, that is actually really cool. So before I tell you what it is, does anybody know what this is a picture of? Yeah. It's not Europa, but close. So this is Saturn's rings. This is the moon Enceladus, and back there, that very dark object, is the moon Titan. And what you're seeing here is the Cassini probe is orbiting Saturn, and it's looking in this direction along this line of sight, and it took this photo. So here's Enceladus here, Titan here, and the rings in between. So I thought this was a really cool photo for another reason, and that's because everything in this photo contains water. So Saturn's rings, which you see here at a different angle, are made of a bunch of tiny little particles, about millimeter to centimeter sized grains of water ice. And throughout the talk, I'm going to use the phrase water ice, and I don't mean anything special about that. It means exactly the same kind of ice you find in your cup, But in astronomy, we find a lot of different kinds of ices, like carbon dioxide and carbon monoxide. So we always distinguish what kind of ice we mean. So these are mostly water ice. And then there's the moon Enceladus, which is made almost entirely out of water ice. And you can see the fissures and this interesting pattern on its surface. And these bright streamers that are coming off the surface of Enceladus are water vapor. So what's happening here is called cryovolcanism. And the water ice is melting and it's being erupted at very high velocities here. So you're getting water volcanoes on Enceladus, which is really cool. And then there's Titan, which is in the back, and it's the largest moon of Saturn. And it has its own atmosphere, which is unusual for most moons. And it actually has liquid on its surface. Now these liquids are not water, unfortunately. They're lakes of methane and ethane. So you might know methane as natural gas that you use to heat your house. But on the surface of Titan, it's actually a liquid. But beneath the surface of Titan, there's actually a lot of water ice. So this is a cross-section of Titan where we've modeled the interior here. So you can see the atmosphere is this blue glowy layer on the outside. The surface is kind of brownish because of all this methane and ethane. And just below the surface here, we have a subsurface ocean. And that's mostly made out of water. And beneath that, we have high pressure ice as well. So we have many examples of icy moons in the solar system. And some of them have subsurface oceans, but none of them look quite like this. None of them have an ocean that's on its surface and visible from afar. And the reason I really want to find an ocean on the surface of a planet is because this is really the only way, without physically going to a location, where we'd actually be able to see if that planet had life. That life has to be on its surface, not buried beneath a thick layer of ice in a subsurface ocean. We won't be able to find that life from afar. But if we could find a planet like this, one that has a surface ocean, then we might have a chance of determining if that planet had life. So what makes the Earth different? Well, I'm going to talk about that more in a bit. But one of the things that makes it different is that it's in this special orbital region around the star. And we call this the habitable zone. And the habitable zone is really the orbital region where liquid water is stable on the surface of a rocky planet. And that region is highlighted here in that fuzzy green band around the sun. And so within this region, we would expect that a rocky planet would have liquid water on its surface. And you see that the Earth is right kind of in the middle of that zone. But we have two other planets in the habitable zone. We have Venus, which is closer to the sun than us, and Mars, which is further out. And so in the next section, I'm going to talk about the differences between these two, because we know that Venus doesn't have any water. And Mars might have had water, but it really doesn't anymore. So what makes them different? That's what the next section is going to be about. But just to recap what we've talked about so far, I've told you about why I think water is special. It's a polar molecule, which allows membrane formation, which helps life. It has a stable environment because the solid floats in the liquid. And it's liquid at a very broad range of temperatures where organic chemistry and life can occur very happily. I've shown you a lot of places where water exists throughout the solar system, but mostly in ices. So far we haven't really found surface liquids. And then I told you a little bit about the habitable zone, which I'm going to come back to in the next sections. But in the meantime, are there any questions?
How do you find evidence of the subsurface oceans?
The question was, how do we find evidence of subsurface oceans? Well, one way is by seeing eruptions like we saw on Enceladus. There are a number of other moons that also erupt and have geysers. Another way is that if most of these oceans actually have a lot of salt in them, just like our ocean does, and that makes them electrically conducting. So if they are moving around, they form a slight magnetic field. We can detect that magnetic field.
That is a question.
That was the question. Any other question? Yes.
Now, some planets in our solar system have magnetic fields that don't have this ocean. So how do you tell the difference between kind of the magnetism you described and the kind that we see in some of our other planets?
The question was, how do other planets in the solar system have magnetic fields as well? So how do we tell the difference between one caused by an ocean and one caused by other effects? So most of the rocky planets, aside from the Earth, do not really have magnetic fields. The Earth is kind of special in that regard. The reason the Earth has a magnetic field we know pretty well is because we have an iron core, and the outer part of that core happens to be liquid, and so it's convecting, and it's also an electrical conductor, and that's what creates our magnetic field. And it's much stronger than the magnetic field of these icy satellites. So the thing that we also know about these icy satellites is we have chemical compositions for their surface. So we can look at their surface and see that there's ice there. And we can also, as I'll come back to when I talk about exoplanets, we can measure their densities. So we know their physical size, their radius, and we know their mass. So we know that they're mostly made out of water because that's much lower density than rocks and metal are. So we kind of have to piece it together from a bunch of different lines of evidence. Are there any other questions? Yes?
So you just touched on it. How does one measure the mass of those exoplanets?
I will get to that in our third section, actually.
Yes, the subsurface water on the moon.
On our moon,
Yes.
there is a little tiny bit of water on our moon, and it's mostly in ice. So, but it is not an ocean. There's not enough water on our moon to form an ocean. So our moon, we can measure the mass, and we know its density again, and it's much denser than Enceladus. It's mostly made out of rocks. Okay. If there are no other questions, all right. So I'm going to move on then, and I'm going to talk about Goldilocks and the three planets. So the reason I've called this that is the habitable zone is often referred to as the Goldilocks zone because it's the region where it's not too hot, not too cold, it's just right. But in our solar system, we have these two planets, Venus and Mars, and one of them actually is too hot. So that would be Venus. And the reason it's too hot is because it's much closer to the sun than us. It doesn't look like it here, but it receives significantly more light than we do. And so it has a thick atmosphere now. Now we think it probably started out with about the same amount of water as the Earth did, and unfortunately it suffered a runaway greenhouse effect. Now you've all probably heard of the greenhouse effect with regards to global warming. So what the greenhouse effect is that an atmosphere actually blankets the surface of a planet and causes it to warm up. Without our own atmosphere, the Earth's surface would be on average about 50 degrees cooler than it is today. So gases in the atmosphere trap radiation from the sun and don't allow it to escape back up to space, and that warms the surface. Now, Venus was just close enough to the sun that this happened in a runaway fashion. So the water that was on the surface of Venus, might have been on the surface of Venus, went into the atmosphere. And water vapor is actually a very good, very strong greenhouse gas. And so that caused the surface to warm up even more. And so that drove even more material into the atmosphere. The atmosphere of Venus today is made mostly out of carbon dioxide. And these clouds that you can see, these features, are made out of sulfuric acid. It's a very inhospitable place. This is an image of the surface of Venus taken with radar, so it's peering through the clouds. And the surface pressure here is like being under about 3,000 feet of water. It's 90 times our atmospheric pressure. And the surface temperature, because of the runaway greenhouse effect, because there's so much carbon dioxide in the atmosphere, the temperature on the surface of Venus is hot enough to melt lead. So there's no chance of finding liquid water on this planet. Now, if we go further out into our sun's habitable zone, we have Mars, which is on the other side of the spectrum. It's too cold. Now, early in Mars's lifetime, it actually might have had a fair amount of liquid water. It was a little bit warmer, the interior of the planet was warmer, and it had more of an atmosphere. Its atmosphere was definitely thicker back when it formed about 4.5 billion years ago. And we can see features on the surface of Mars that look like there was an ocean covering most of the northern hemisphere. But unfortunately, Mars is further away from the sun, and so it's also a much smaller body. And it has no magnetic field, which protects an atmosphere. And so the combination of the distance from the sun and the lower gravity, because it's significantly smaller than the Earth, meant that it couldn't actually hold on to its atmosphere. So the atoms that are in its atmosphere, which included water vapor and carbon dioxide and other things that make up our own atmosphere, Mars was actually too small to hold on to those. So radiation from the sun actually accelerated those atoms fast enough that they flew off into space and never came back. So we think that atmospheric loss from solar wind might be why Mars no longer has these oceans that it used to have. Now that brings us back to the Earth. So the Earth happens to be just right for us. Now it has, and it's the only planet that we know of that has this surface ocean. So what makes it special? Well, one of the things is its temperature. We're at the right distance for water to be liquid on the surface. We have just enough atmosphere, but not too much. But the geology of the planet also has a role to play in whether the Earth has water on its surface or not. So this is a cross-section of the Earth. And I told you a little bit before about our core. So this inner core and the outer core are made out of iron metal. The outer core is liquid, and it convects, which creates our magnetic field. And that magnetic field helps to protect our atmosphere from radiation that might otherwise strip it away. So that's a fortunate thing. And then we have the mantle, which is made out of rocks. And then on the surface, we have a thin layer that we call the crust. And it's about the thickness of the line here, so it's actually not shown. The region of space on the Earth that we actually interact with is very small. Now on the Earth's surface, we're talking about water. We have one ocean mass of water. I'm just going to call it an ocean mass. But the Earth has a lot more water than that, actually. The surface, the rocks in the mantle, contain somewhere between 1 and 10 times the amount of water that we have on the surface. That water is trapped in the chemical lattice of the silicates, the rocks that make up the mantle. Now, how do they get down there? Well, the Earth has what we call plate tectonics. It's a very unique geology in the solar system. Venus and Mars do not have plate tectonics. Plate tectonics is the crust is broken up into these individual little sections that move on their own. They move independently. So North America is actually drifting towards the Pacific Ocean. And you may have heard of the Ring of Fire, which is a region around the Pacific Ocean that has a lot of volcanoes. And the reason for those volcanoes is because of plate tectonics. And what's happening is we have two different kinds of plates on the Earth. We have continental plates, which is what we live on, and then we have oceanic plates, which are all covered with water. And these plates shift around, but oceanic plates are actually very young. Continental plates are pretty old. They're almost as old as the Earth itself. But oceanic plates get destroyed and created constantly. So oceanic plates sink beneath continental plates in some regions where they are very dense and heavy, and they sink into the Earth's mantle, and they get destroyed down there. But new ocean plates are constantly being created at volcanic centers in the middle of these oceanic plates. So subduction destroys these ocean plates, and then volcanism creates these plates. And water goes along for the ride. So I told you that these oceanic plates are all covered with water, and water gets trapped in sediment grains, like the sediments on top of this plate, and it seeps down into the rocks down here. And that water is then transported back deep into the Earth's mantle through subduction, and it gets brought back to the surface through volcanism, like the volcanism we find around the Pacific Ocean, and the volcanism that's creating the oceanic plates. Now here's where my research comes in. I have taken models for the Earth where we try to figure out how this has happened over geologic time. That is from the Earth's formation to the present day. And we use mathematical models that calculate the way the Earth cools down, the way its mantle temperature drops over time, and then try to also couple that to the rate of plate tectonics over time, and with it, the rate that water gets exchanged between the surface and the interior. So the Earth's mantle is cooling off over time. So what do you think is happening to the surface water abundance? It's being exchanged between the interior and the mantle over time by plate tectonics. Anybody want to hazard a guess? Okay. Well, we had a lot of water on the surface early in the Earth's history, and as the mantle has cooled off over time, that water gets transported back into the mantle. So eventually, at some very long, great age, all of the water that's on the surface of the Earth will get transported back into the mantle, and the surface of the Earth will be dry. There will be no water left. But that will happen a long time in our future. But we started out with an early, very wet history, and we're slowly losing water to the mantle over time. So in my research, what I'll be doing is taking these models for the Earth and applying them, hopefully, to new planets that we're finding outside of the solar system. And I'll tell you about that in a moment. But in the meantime, let's recap a little bit. So I told you about Venus and the fact that because it's a little bit closer to the sun and it's a little bit hotter, it suffered a runaway greenhouse effect, and now it's too hot to have liquid water. And how Mars is a little bit too small and a little bit too cold to hold onto its atmosphere, which allowed it to have water in its past. And then I told you about the Earth and about our special geology and plate tectonics, and why that allows us to have water on the surface right now. So, are there any questions about that? Yes?
Where did the water on the Earth come from in the first place?
The question was, where did the water on the Earth come from in the first place? Well, there are pretty sophisticated models nowadays of how planets form. So the way planets form is the star is collapsing from a giant cloud, giant molecular cloud, and the material around it flattens out and it forms a disk. And it starts out really hot. And all of the elements that you find in the sun and in the Earth are found in this disk. And eventually it starts to cool off and everything starts condensing out, making solid materials. And those solid materials run around this disk and they hit each other. And eventually they grow really big, and we call that accretion. So there is a line in this disk, a temperature line basically. So the closer you are to the star that's forming, the hotter you are. And as you move out, you get more, you get colder. And so water can condense at a certain radial distance out from the star. And we call that the ice line, or the water line in the solar nebula. And material outside of that has water ice that can condense. And so that water ice can get trapped into these forming planets. So we actually think that the water was accreted, as we call it, accreted to the Earth when it first formed. And that it was actually trapped inside those rocks when it formed. Is there any other questions? Yes, over here.
So how is, it sounds like your work has to do with tectonics, but you said which there are other planets out there that have tectonics and you're like research.
Yes, so I'll tell you, yes, so we found a lot of planets outside of the solar system, and a lot of them happen to be rocky, and some fraction of those might have tectonics similar to the Earth, or at least there's no reason to think that the Earth has to be unique in this respect. Yes?
So we talk about Mars losing its atmosphere, it's too small to keep. So how can it attract it in the first place?
Well, it was accreted to the planet in that primordial, when that planet formed, right? So it was delivered to the planet when it formed. There is actually still water on Mars, right? It's mostly in ices. So the Mars has polar caps, which you can kind of see here. Most of that is actually carbon dioxide ice, but there is a significant amount of water ice there. We actually think there's water ice under the surface as well. But Mars doesn't have a thick enough atmosphere for that to actually be liquid at any point on the surface. Earlier in its history, Mars's interior was hotter. So if I go back to this slide, you know, all planets start out hot, and they gradually cool off over time. Small planets cool off a lot faster than bigger planets. So Mars cooled off much more quickly than Earth did. So it's possible that this process, the return of water into its rocks, happened much more quickly on Mars. There a question? Yes, sorry.
Yeah, back to the previous one with the two
Yes.
graphs. Does the actual return of surface water into the mantle speed up the cooling process, or is just not enough water for that to have an impact? For Earth, say, or for Mars?
So we actually think the Earth is at kind of a stable point. So the addition of water to the mantle, as I'll talk about this a little more later, water actually affects the viscosity, which is one of the properties that dictates how the mantle convects and how it cools off. So the more water you add into the mantle, the lower the viscosity is, and the faster it cools off.
Okay.
So there is actually a kind of a balance here. Yes?
Is it possible to tell whether or not an exoplanet has a magnetic field?
The question is it possible to tell if an exoplanet has a magnetic field? Right now, no, there is not. There are thoughts about how to do this for very large exoplanets that are very close to their stars. They may have strong emission in certain wavelengths of light, like radio waves, that produce auroras, like we see the northern lights on our planet. Giant planets may have very strong auroras, especially if they're very close to their stars. So we can try to look for those, but so far we haven't really been successful with that. And we really don't have the resolution to try to do it for smaller planets yet. Okay, so this is our middle question break. So I think right now we're going to take our intermission. It'll be about 10 minutes, and when we come back, I will tell you about how we find exoplanets, and after that, I will tell you about how my research applies to those planets. Great. Right. So if you look at the abundance of carbon dioxide that we see in Venus's atmosphere and that we know is trapped in rocks on the surface of the limestone, it's about the same amount. So one of the things that happens on the Earth is because we still have liquid water, we have a cycle that we call permeability cycle. So carbon dioxide that's in the atmosphere and mixes up with rain. It falls and it makes a carboxylic acid, carbon acid, and that falls on the rocks and it weathers that material away and it forms carbonated minerals that then get washed into the ocean and get sequestered in these giant thicknesses of carbonate minerals. Limestone. Right, the cliffs of Dover, yes, exactly. Yeah. So the carbon dioxide gets sucked out of the atmosphere through this cycle, and it gets sequestered in the rocks. And that means that the atmosphere has less greenhouse warming, right? So the surface temperature of the Earth kind of gets sort of buffered this way, so it kind of maintains a fairly constant amount of CO2 in the atmosphere. Right. Yeah, exactly. So the water, because the atmosphere might start out about the same as yours, but it's just a little bit closer. surface temperature had no water. And so that water got turned into steam, and then it increased the amount of warming, so the surface temperature got even hotter, and any water that might have still been there is now in the atmosphere. And now there's no rain out. That's why it's
All the other libraries that like back, they're the same.
right.
Okay. I wasn't quite sure.
Sure. Okay. No, it's pushing it out. Somewhere down the line. I mean, the sun is getting brighter. And there was yes. I mean, we're talking about it's not scary.
Kind of did we were just like, basically,
water.
Right.
But all this is
so more info.
So we eventually get stable, the same amount of water that you're down.
It's kind of stable right now. So there's going to be a
It takes time to get out of that relationship.
I don't know.
That too. But this is very information. Yeah, but Greenland is interesting. So there's a
Just remind me of just to say, just let you know, just put it out there. Right. I would totally say that. you like
It
go
was-
over it, but then
The name of it has
would you like that
changed.
snack? So I would like just take a couple minutes and it would be eating away at the end. And then you like, well, I got it. Let's do it about.
Yeah. Okay, I hope everybody had a chance to get some water or cookies. So now I'm gonna actually tell you about exoplanets and about our hunt for exoplanets, what they are and how we find them. So just a brief overview, exoplanets are planets orbiting stars other than the sun. And we have found many exotic kinds of planets that we don't see in our own solar system. So some of these kinds are hot Jupiters. So this is a planet made mostly out of hydrogen and helium gas, similar to Jupiter, but it is so close to its star that its orbit, its year, only takes about 20 hours. Now these planets can range from about 20 hours out to about 3 to 5 days. But we found quite a few of these guys. And another kind of planet that we don't have in our solar system are mini Neptunes. So these are planets roughly 5 to 15 Earth masses that are mostly made out of probably water, but mostly in an ice phase. So not quite what we're looking for. So the thing about exoplanets is that we can only ever look at them remotely. We'll never actually be able to travel to an exoplanet in order to study it. And so we have to infer the presence of water or life by looking at their atmospheres. And this is one of those reasons that I really want to find a planet that has a surface water ocean. Now, how do we find these planets? There are two main detection methods that have found the majority of the exoplanets to date. So the first I'm going to talk about is the Doppler method, Doppler Shift. So what happens is that as a planet orbits a star, the star does not stay in a fixed location. The star is also orbiting a point that we call the center of mass, which is slightly offset, and here it's exaggerated slightly, but slightly offset from the center of the star. So the star is actually on its own orbit, and the size of that orbit is related to the mass of the planet that's orbiting it, and the distance that planet is from the star. And Doppler shift means that as we're looking at the star, as it's rotating in its orbit, the light from the star is shifted in wavelength. So as it's coming towards us, it's blue shifted. And as it's going away from us, it's red shifted, or the wavelengths of light are become longer. So blue shifted means they're becoming shorter, red shifted means they're getting longer. So we look at the star, we can't actually see the planet necessarily in this configuration. And we look at the star and we can measure how much this is happening, and that lets us measure the planet's orbital period, so how far away it is from the star, and the planet's mass. The second method is called the transit method. And in this method, what we're looking at is a star and a planet that's orbiting it, And the orbit of the planet happens to be lined up coincidentally with our line of sight. So that when the planet passes in front of the star, it blocks a little bit of the light from that star. So if we're monitoring the star's brightness, we see it's a normal brightness, and then as the planet passes in front, we get this dip. So this doesn't really tell us anything about the planet's mass. It does tell us, again, the period of the planet's orbit, so how far away it is from the star, and it tells us about the physical size of the planet, or the planet's radius. Now, with these two methods, we get mass and we get radius, or physical size, and that tells us about the density of the planet. And densities can tell us a little bit about composition, as I was talking about during the question section. So low densities mean that the planet is mostly gas. So Jupiter has a density of about 0.9 grams per centimeter cubed. Intermediate density means it's mostly water or intermediate kinds of materials. Now, water has a density of about 1 gram per centimeter cubed. And high densities mean that the planet is made out of heavier elements that make up things like rock and metal. So the Earth is made mostly out of rock and metal, and its density is about 5 grams per centimeter cubed. So that's what we're looking for. We're looking for planets that have high densities. And those will be the planets most similar to the Earth in composition. Now, I'm going to show you, here's the number of exoplanets that we have detected by year. So the first exoplanet was detected in 1989, and it was alone for quite a while. The second one, you probably can't see it here, is in 1992. And we have only a few planets for about 10 years, a handful of planets. And all of these planets are hot Jupiters. So these are the very massive planets on very close orbits. Because this is what our detection methods are most sensitive to. Close-in planets that are really big. As our techniques got more sophisticated, though, we started finding more and more planets. So some of these planets are on further orbits, and the planets that we were finding got smaller and further away from their stars. So prior to about 2011, most of the planets we had found were by the Doppler Shift method, or here it's referred to as radial velocity, so shown in the red. So those kinds of detections are all done from ground-based telescopes. And so we have to deal with issues from looking through the Earth's atmosphere, which causes a lot of noise in our measurements. So it limits the size and the distance of planets that we can actually find. Now, transits became, you can do transit observations from the ground, but where they have really shined was with the Kepler Telescope. And that is the cause for this enormous bump here in 2014. Kepler was operational from about 2011 on. It's no longer operational in its original configuration, but it's still working a little bit. So to give you an overview of the Kepler mission, it was a space telescope that was using the transit method to find exoplanets. And what it did was it looked at one single little patch of sky. And in that patch of sky, it picked 100,000 stars to look at. And it looked at those stars for 4 years to try to observe transits. And in those 4 years, we have more than 1,000 confirmed planets. If I go back to that previous slide, you see that prior to 2014, we had less than 200 planets. But now we have an enormous number of confirmed planets, and then we have 3,500 additional candidates that are awaiting follow-up. Unfortunately, we probably won't be able to follow most of these planets because the stars that they orbit are too faint and too far away to get good observations of them from the ground. So we would need another space telescope to follow them up, which unfortunately is not in NASA's budget for us. Now, the planets that we have found, so Kepler was looking primarily at sun-like stars. Now, you might not be aware, but stars come in lots of different masses and temperatures. So the sun is kind of an average star. Here it's at the top of the graph, but it's an average star. The largest number of stars in the galaxy, though, are actually quite a bit smaller than the sun. They're smaller and cooler. And the habitable zone of a star depends on how hot that star is. So if we're looking at the amount of light the planet gets, then habitable zones will be closer in or cooler stars. And since our methods for detecting planets are biased towards smaller or closer in planets, these are our best options for finding planets within the habitable zone of stars. So coming up, I'm going to tell you about the planets that we have found in the habitable zone. But let me just recap a bit. So I told you about the two detection methods that we've used to find most of the exoplanets. Those are the transit method and Doppler Shift. And the most successful transit detector has been the Kepler Space Telescope. And we're looking for planets that are in the star's habitable zone. And I'll tell you about the planets that we have found there in the section coming up. But for now, do you guys have any questions about these detection methods? Yes?
I know a lot of stars are really star systems, or two or more stars orbiting together. Does Kepler, do you guys working there, do you exclude those, or can you compensate for the fact that the planet could be near two stars and then close to one, and how it shifts throughout its orbit?
Right, so the question is that a lot of stars are actually not singles. They tend to occur in pairs or actually in triplets. And does Kepler account for those things? And the answer is yes. So it is true that most stars are actually not alone. Most stars have a companion, another star that orbits them. And Kepler has, in fact, found a number of circumbinary planets, so planets that are orbiting two stars at the same time. One of the reasons that we have so many planet candidates is because in order to confirm that they are not just, a pair of stars orbiting each other, or one star orbiting a planet orbiting maybe a smaller star than we think it's orbiting, or if there might be actually two stars in our aperture that we're seeing. So that's why there's so many candidates, because we haven't been able to actually go through and look at every single one individually. Quite frankly, it's very expensive with telescope time to do that. And again, most of those stars are too faint to determine if there actually is another star in that field. Yes?
So you said that the transit discovery method depends on planet essentially blocking our view of the light. So
right.
How lucky are we that most of those planets are on the same plane of our vision for our looking?
Right. So the question is, if you have to find if you can only find a transiting planet, if it happens to be, aligned with our line of sight, does that just mean we're lucky? And we think you can determine the probability that a planet will transit if you assume that all planets are kind of oriented randomly in different orientations, and we find about the number that we were predicting. But so from the number of planets that we've detected, we can actually figure out well, how many other planets are there that we just can't see because they're not going to the line of our sight, right? So that's one of the big things that Kepler has done, is try to determine the occurrence rate of planets around stars. And it's actually, there are so many planets that we see that we think that basically every star has at least one planet. Now we don't see stars, we don't have 100,000 planets. We looked at 100,000 stars. We don't have 100,000 planets because they're not all lined up to our line of sight. So that was one of the reasons for Kepler's, the design of the Kepler mission was, in order to find enough planets to do the proper statistics on them, we knew that we had to look at a lot of stars for a long time to figure out what the actual occurrence rate of those planets are. Yes?
So without Kepler, I would imagine that most of the next set of exoplanets we detect would be back to the Doppler method. But with that, how small of a planet can you detect? And also, like, what's your level of confidence for systems with multiple planets that would be kind of tugging in its own direction?
Right, okay, so the question is, if we couldn't look at planets with Kepler, if we didn't have that detection capability, what's the limit of what we could do with radial velocity? So the signal for, so we measure the Doppler shift in velocities, so speeds, meters per second is the unit that we use. And Jupiter produces a signal of, probably getting this wrong, I think it's about a meter per second. And we can do that with current technology. But Earth, at Earth's orbit, produces a signal of only 10 centimeters per second. And that is at the very, very limit of what we can do right now with ground-based telescopes. Now there are new telescopes coming online that will be able to push that limit a little bit lower. But right now, we're limited by a lot of systematic noise from stars and just the resolution of our telescopes. So with the next generation of telescopes, these really large telescopes that are going to be coming online in the next 10 or so years, we might be able to detect an Earth-like planet in an Earth-like orbit, but it's going to be a lot of hard work to get there. Yes?
How was the region of space picked for the Kepler mission? Was it a random thing, or did you guys have an idea?
It was not random. I don't really know a whole lot about why it was selected. I think it has to do with the region of, it's slightly above the main plane of the galaxy, and slightly away from the center of the galaxy, where there's a lot of very energetic things going on because of the black hole at the center of our galaxy. So yes, there was a lot of thought put into where particularly to look. All right, so I think I'm going to move on. And now I'll talk about super exorecord planets, minor water. Okay, so what I'm going to talk about mostly are super Earths, and I'll talk about why in particular super Earths, tell you a little bit about their internal properties, and then apply that model that I was telling you about for Earth's deep water cycle, how the water changes throughout history, and how we applied that to super Earths. Now, why super Earths? Well, it turns out they're actually really common. So this is another kind of planet that we have no example of in our own solar system that happens to be really common on other kinds of stars. So in this figure, this is a histogram that shows different sizes of planets. So here we have Earth size, that's less than 1.25 Earth radii. So that circle with a plus in it means Earth. And then there's super Earth, which are 1.25 up to 2 Earth radii, Neptune size, and then Jupiter size or larger. Now you can see that pre-Kepler, when most of the planets we had detected were done by radial velocities, we found a lot of really big planets. And again, that's because they're really big, so they have a much larger signal, and most of these are really close to their stars, which makes them even easier to detect. But the most common thing that Kepler found was, well, it found a lot of Neptunes, and it found an awful lot of super-Earths. So these are planets that are 1 1/4 up to 2 Earth radii. Now, unfortunately, Kepler can't measure a planet's mass. So we have to try to follow up some of these planets with the Doppler Shift method in order to figure out what these are actually made out of. Because it's possible that they're not made out of rock and metal like the Earth is. They could be made out of gas and ice like Neptune is. But so there's been a lot of follow-up work. We've actually found a number of rocky super-Earths. And some of them happen to be in the habitable zone. So this is another graph, like I showed you before, that shows how the habitable zone changes. So this is changing in a slightly different way. Here we have, so there's stars hotter than the sun. The sun is this star here. And then we have cooler stars. And we have here Venus, Earth, and Mars. And here this is the effective stellar flux where Earth gets, so everything here is normalized to the amount of light that Earth gets. And the boundaries for the habitable zone here are, this is the inner edge, here this red line, and then the blue line here is the outer edge. So you can see again, the Earth falls right in the middle of the habitable zone, and Mars is here on the outer edge. And these are all the exoplanets, or some of the exoplanets we have found inside of habitable zones. And the sizes of these planets here is their relative size, their size relative to the Earth. So the Earth is actually one of the smallest objects here in the habitable zone, right? So if we want to think about, if we want to start detecting and looking and characterizing planets inside of habitable zones that might have water, we're going to first have to look at larger planets than the Earth. So we have to try to think about what things might be different on these larger planets than on the Earth, and how that might affect the presence of water on their surface. So these are all inside the habitable zone, and so their surfaces are probably at about the right temperature to keep water liquid. But now we have to, again, consider the geology. So if we think about planets like the Earth, and if they have plate tectonics, then how does their deep water cycle function? Does it work the same way as it does on Earth? So in order to do that, we've taken that model for the Earth that I showed you before, and we're trying to apply it to super-Earths and see if it might be different. And the reasons it might be different are because of the physical properties of the materials that these super-Earths are made out of. So I talked a little bit before about viscosity. Viscosity is the property of how quickly material can flow, and this is what controls the rate at which the planet's interior is cooling down. So I showed you that temperature, that graph before of how the internal temperature decreases with time. So a material that is more viscous will cool off slower, and a material that is less viscous will cool off more quickly. Now, here's some figures showing the viscosity of common substances. So this is, the viscosity of water is about 1. It's our standard for basically everything. So here's this lovely water fountain. And then I have this lovely chocolate fountain. And the viscosity of chocolate is about 40,000 times that of water. And then here I have this really cool lava fountain. And the viscosity of this is 10,000 up to 1,000,000,000,000 times greater than water. And the rocks in the Earth's mantle actually have viscosities even higher than this. So 1,000,000,000,000 times higher than that of lava. So viscosity determines how quickly material can can flow. But viscosity itself depends on the pressure and temperature that the material is experiencing. So those mantle rocks are very hot as the temperature increases as we go deeper into the Earth. And the viscosity decreases as temperature increases. But we have this competing effect that pressure causes viscosity to increase. And super Earths are going to have much, much higher pressures than the Earth does. So the pressure at the Earth's core mantle boundary is 1.3 million times the pressure at the Earth's surface. And the pressure at a super Earth's core is 15 million times the Earth's surface pressure. So that has a pretty strong effect on the viscosity of the planet. But the temperature is also increasing, so we actually have to do the models, we have to do the calculations to figure out how this affects the way that the planet cools off over time and how that drives the water cycle. The other property that also affects this is gravity. So gravity obviously increases with the planet's mass. Now, the gravity of the moon is about 1/3 of that of the Earth, and the gravity of a super Earth, about 5 times more massive than the Earth, is about twice that of the Earth itself. And this will also affect how that material can move about in the mantle of the super Earths. So now I'm going to show you what my research was. I took this model for the Earth's deep water cycle, and I calculated the history of the oceans for these larger planets. And I'm going to show you these calculations on a series of these graphs. Now, what this is showing is for a 1 Earth mass planet like the Earth and a 5 Earth mass planet, the level that the water would have on the surface. And this is an elevation profile for the Earth. Now, the Earth's peak elevation is about here. That would be Mount Everest. And our lowest elevation is about here. That would be the Marianas Trench. So here is about the average depth of the current ocean. And this is about the average height. This is about sea level. So modern day sea level is at 0 kilometers. Now, super Earths have a slightly squished elevation. They have less change in their elevation overall because their gravity is stronger. And so rocks have kind of a constant material strength. And because the gravity is stronger here, you cannot get as much uplift or rifting as you can on the Earth. So we've got less elevation here on the larger planet. And now what I'm going to show you is a series of time steps from the time of the planet's formation to about 10 billion years, which is about the length of the lifetime of a star. And the blue area will show you what the abundance of water is on the surface of the planet. So here we go. So Earth has, at about 1 billion years, remember the Earth is very hot in the beginning, and it has a lot of water on the surface because it's very hot on the inside, and so it's got a lot of volcanic outgassing. So water that was trapped in the interior during its formation is released very rapidly. In contrast, the super Earth has very little water initially. That's because it's actually, at this point, not really hot enough for volcanism to happen. Because the pressure in its interior is so high, it takes, the temperature has to be hotter for melting to happen on the super Earth than it does on the smaller planets. So as we go through time, the amount of water on the super Earth gradually increases. And here's about the age of the Earth. We have about surface, about present day water on the Earth. Not exactly right, but we weren't really trying to match the Earth for these models. And you can see over here on the super Earth It has less water overall, but it has far less elevation, so it doesn't have much dry land left at all at this point. And so as we keep going, the Earth's water decreases over time, whereas the super Earth is kind of stable but still increasing slightly. And so here at the end of the star's lifetime, the Earth has a lot of dry land. It's still got some water, but the super Earth has only the very highest mountains are still exposed. Now this can be certainly life on a planet like this with very little exposed life is going to be very different than it would on the Earth. And this might be problematic even for the surface temperature of the planet. As I was discussing with somebody earlier, the amount of carbon dioxide in a planet's atmosphere is actually somewhat buffered by the amount of water on the surface. So water in the atmosphere reacts with carbon dioxide, and it rains out onto continents, and it weathers the rocks away. And the carbon dioxide gets transported and trapped into sediments as carbonate minerals. If you don't have much exposed land, you're not going to be able to draw down very much carbon dioxide, and so you'll get a buildup of CO2 in the atmosphere, which is going to warm the planet up. And so this planet might actually get too hot to maintain that liquid ocean. That's work that needs to be done in future modeling, is to look at how the atmosphere of these planets actually evolves along with the oceans. Okay, so, but this is actually promising. If we're looking for planets that have liquid water, this means that if a super Earth has tectonics the way that the Earth does, then we would expect it to have a very long-lived ocean. And so we might be able to try to detect it. So how will we detect an ocean on a super Earth? There's one proposed method, which is relies on ocean glint, which is what you see here in this very bright patch. So what happens is that liquids reflect light preferentially into certain directions. And we can try to use that brightening to try to detect the presence of liquid water. This has actually been done for Titan. Remember I showed you that picture earlier that Titan has liquid methane lakes on its surface. And you can see here right at the North Pole, this very bright patch. And that's a reflection coming off of this methane lake. And this might also be possible for exoplanets somewhere in the future. So here I'm showing you observations that were taken of the Earth. The observations are on the left. And these were taken from LCROSS, which is a satellite that's orbiting the moon. So this satellite turned around and it looked back at the Earth to try to simulate what it would be like for us to look at an exoplanet. And this is a model for what the Earth looked like when LCROSS was looking at it. So here we have mostly the sunlit side. Here we have only a slim little crescent. And here we have about half crescent of the Earth. And you can see this kind of bright patch right here. This is glint coming off of the Indian Ocean right here on the very limb of the planet. So this is work that might be possible in the future. Now we'll have to unfortunately wait for the next generation of space telescopes, possibly with ground-based telescopes. This is the next upcoming space telescope. This is James Webb. It's due to launch in 2018, and it's kind of seen as the Hubble's replacement. It's not really replacing the Hubble. It does something slightly different, but it's going to be able to characterize a lot of exoplanets. And so hopefully we might be able to use it to find oceans on some of these super Earths. So stay tuned for that. So let me just recap really quickly. So I told you in the first section about why we want to find liquid water, why we think it's important for life, and where we have found it in the solar system, in the rings of Saturn and the icy moons of the giant planets. And I told you about the habitable zone and the 3 rocky planets in our solar system and why they are different. And what makes the Earth special is both its location and its geology. And then I told you about the 2 main detection methods for finding exoplanets, the Doppler Shift and the Transit method. Then I told you about the awesome work done by Kepler, finding all of these great targets for future observations. And then I told you about how super Earths might have water on them. So with that, I'll end and say hopefully someday in the future we'll be able to find a little planet like this. So thank you for your attention, and I'll take any Any other questions? Yes.
So are there any other ideas of how we could look at planets that are differently? You talked about is there any other night sky kind of ideas that people are thinking of ways to detect planets?
Ways to detect planets?
Right.
So there are a number of methods that I didn't talk about because Doppler Shift and transits have found the vast majority of the exoplanets that we have found. There are other methods that you can use to find them, like gravitational lensing, which is a very exotic sort of method that looks at the bending of light because of the gravitational field of a planet. Gravitational microlensing has found about a dozen or so planets. They're not really, so the benefit of radial velocity and transits is that we can see them repeatedly, so we can get some idea of what their orbit is. But with gravitational microlensing, it's kind of a one-time deal, because what we're seeing is a distant star is passing behind this planet and star system from our line of sight, and once it passes, it's never coming back. So we can try to look at those with other methods and follow them up. Another really exciting, probably is going to become much more important in the future, is direct imaging. You can actually try to take photographs of some planets. Now these transits and radial velocity are both indirect methods of detecting planets. We're only looking at the effect the planet has on the star. We can't actually see the planet itself in these methods. With direct imaging, what we do is we try to look at very bright, very young stars nearby to us, and we try to block out the light from the star and look for big planets that are on wide orbits around them. And so if they're young, these planets are still pretty hot and they're producing light of their own, so we can try to actually image them. So we found a handful of planets with that method so far, but there's a lot of work in pushing that further, so I think that's going to become much more important in the future. And there are a number of other planet detection missions coming up. There's the TESS mission, which is being led at MIT. And it's going to do something similar to the Kepler mission, but instead of looking at a fixed patch of sky, it's going to look at basically the entire sky for 30-day chunks of time. And it's going to look only at the very bright stars close to us that we can actually follow up from ground-based telescopes. So that'll be very exciting. That'll give us a lot of targets for future observations. So there's a lot of work on trying to figure out how to find more planets, how to find closer, bigger planets that we can actually look at from the ground so that we can follow them up with more resources. Any further questions? All right, if not, thank you guys for coming. This has been fun, and I hope you had a good time.
My daughter graduated. She's in high school.
Oh, well, that's great.
Yeah. She's not so interested in economy, but she's always interested. So,
I have a lever.
I've been watching on it's like pretty good, except that the biology is pretty sus.
Yeah, someone's telling me that.
So I know lasers measuring up the spectral lines. Once you connect to the individual planets, that will show a lot.
Yeah, that would be great if we could actually see them. Yeah, and then we should start possibly try it out, and then so you're looking at differently, basically, I was saying this like star, and you know how to in transit star, what is left is we're having those to put together like
Yes.
an afternoon workshop with all graduate students and also so far we tried with regard to speakers. Yeah, because 5 to 9 definitely was so 5 to 9 that has money that they want to use for like that kind of partner.
I was miserable that last.
I asked for it.
I gave up on that. I took one class and
And
Hey.
class it dropped because it was just too hard for me.
Aww.
So I
Much better.
Yeah.
Software.
This might be the one. This breaks the chain.
Business software.
Okay.
My fault. I said it's on the MIT. Got a business degree in
We went all sides, yeah.
Yes.
Get out of here, don't make them. They don't specifically because the people, most of us just kind of.
Yeah, well,